Okay, I'm going to talk about a number of things today, still on scattering, potential scattering. So let's see, we finished up scattering of identical particles, at least as far as we're going into it. What I'm going to do first is absorptive scattering, and then I'm going to talk about an example, two examples, which reveal something that is very intriguing, namely that if you look at the nth parcel wave amplitude, it has poles in the complex plane at the bound states of the potential, and we'll see that. So let me first do this absorptive scattering business. So as usual, we're talking about Q bar that's spherically symmetric. We had a formula for the scattered wave function, which was minus the sum I to the L root 4 pi 2L plus 1 YL 0 of theta 1 over 2I kr e to the minus I kr plus I L pi over 2 minus e to the minus e to the plus I kr minus I L pi over 2 e to the 2I delta L. And this delta L is really, delta L is a function of K. Now, so this was the thing, this was the general case. Well, this was the case for elastic scattering. But now what we're going to do is we're going to let this thing become complex. And when it does, then e to the 2I delta L, we're going to call eta sub L, and we can still write it as 1 plus 2I e to the I delta L sine delta L. But now, when it's complex, we can have eta sub L can be less than or equal to 1. Of course, it could be greater than 1 also if delta had a large negative imaginary one. Now, the scattering amplitude is, I think this is online, this chapter, these notes. But the other notes that I'm about to describe are not yet online. The notes about the poles in the S matrix. So then this is eta L minus 1 over 2I. So that's, and this eta L minus 1 over 2I, this is the same thing as e to the I delta L sine delta L. So all I've done is write this scattered, well, remember we have the scattered wave is the part that's e to the I kr e to the 2I delta L, where we write e to the 2I delta L as 1 plus 2I e to the I delta L sine delta L. The one part gives you the incoming wave, the incoming plane wave, and the rest of it gives the scattering amplitude. And if you write eta L as e to the 2I delta L, then what you get is the same formula that we had before. Okay, well, delta sigma elastic, d sigma elastic, the remaining length is fk of theta times the value squared. All right. Now, the total elastic cross section sigma EL, as before, is pi over k squared sum L equals 0 to infinity 2L plus 1 minus eta L squared. So this is
what we had before. It's just that we're writing in terms of eta L instead of delta L, and we're allowing delta to be complex. Okay, so what is the situation where you have total absorption? Suppose we have total absorption. By the way, one of the hardest parts of my preparing these lectures was spelling absorption correctly. Absorb has a B, absorption has a P, and this is, thank God for computers and spellers. Anyway, suppose you have total absorption in L partial wave. Okay, then what's the situation? Then we have eta L actually equal to 0. Okay? So in other words, suppose this becomes so complex that is to say the imaginary part of delta L is sufficiently positive, in fact it goes to plus infinity, delta L goes to I infinity, eta L goes to 0. What is the elastic scattering cross-section? Well, sigma EL in that case, eta L is 0, is pi 2L plus 1 over k squared. So in other words, it's positive. So this is a purely quantum effect, and it's called shadow scattering. So this is called shadow scattering. And the reason it's called shadow scattering is that if you do a real problem, instead of just letting delta become complex, you actually analyze the case with absorption. And by absorption, what we mean here is that the initial beam of particles, some of them do not scatter elastically. Instead, they combine with the target and form something else as an outgoing wave. In other words, what shall I say? For example, a photon scattering off an atom. Okay, it can scatter elastically off an atom. But it could also come in and knock an electron out of an atom. That would be inelastic. And in some of those cases, the photon is absorbed and the electron goes out. The final state is then an electron and an ionized target. So in these cases, or other cases that might be more appropriate, a proton on a heavy nucleus at low energy, you'll have elastic scattering. And then as the energy goes up, you're going to be able to have the proton split apart the nucleus. Or the proton comes in and interacts with one of the nucleons and produces pions. And so you have the initial final state is the initial proton plus a few pions. So all these other states are not elastic scattering, and yet what you find is that the elastic scattering cross-section is not 0, even in the limit where the absorption is total of the L partial wave. And this is called shadow scattering. One of the reasons is that when you look at it either experimentally or in detail theoretically, what you find is that this elastic scattering is peaked in the forward direction, and the bigger the target, the narrower the peaking in the forward direction of the elastic scattering. And so we saw last time that when we looked at scattering off a Coulomb, off either a Coulomb potential or off a Yukawa potential, that the scattering in high energies was peaked in the forward direction. Well, here you see it's going to be super peaked in the forward direction because absorptive effects are going to produce shadow scattering in addition to the forward scattering that we saw in the purely elastic mode. Okay. Now I'm wondering I'm wondering whether to actually do the rest of this on shadow scattering. I think, all right, here's what I'm going to do, because I want to get through this other stuff, which I think is more interesting. These notes are online. I'll just tell you what the bottom line is. If you do a sort of analysis of this in terms of probability currents, so let me give a very abbreviated version of this. If I can finish these notes before the end of the hour, then I'll come back and do this in detail. But I don't think it's that interesting.
What is the sigma absorption in the L partial wave?
So I should have said this was the L partial wave. That's the elastic. That's the elastic in the limit eta L equals 0. The general L partial wave absorption cross section here is pi over k squared times 1 minus eta sub L squared times 2L plus 1. And so what you can see is that this is I wrote this here as sigma elastic L wave minus eta sub L squared pi 2L plus 1 over k squared. But that is just, I think I actually made a mistake here. This formula is correct. Let's drop this one because what I was using here was this formula in the limit of eta L equals 0. So let's leave that out. Let's now look at the total cross section. Sigma total, and again the L partial wave, is going to be sigma elastic. Well, no, actually I'm going to do all the partial waves. So this is sigma elastic plus sigma absorptive, and that's going to be pi over k squared, sum L equals 0 to infinity, 2L plus 1. And now, the elastic cross-section is this one, 1 minus eta sub L absolute value squared. And then we get the absorptive, which is this, 1 minus eta L squared. Now, if you just multiply that out, what you find is that this is equal to pi over k squared sum 2L plus 1, 2 from 1 plus 1. Then you get the absolute value of eta L squared from this term canceled by that, so that one goes away. And so the only thing you get here is minus eta L minus eta L complex conjugate. And so finally, this thing is equal to 2 pi over k squared, sum L equals 0 to infinity, 2L plus 1 minus the real part of eta sub L. Okay. So that's what the total cross-section is. And now, once again, if you look at the imaginary part of the forward scattering at theta equals 0, and you look over here, this guy is square root of 2L plus 1 over 4 pi, so this just gives a 2L plus 1. Then you want to take the real part of this, and so what you get is that this is 1 over k, sum L equals 0 to infinity, 2L plus 1, 1/2 real part of 1 minus eta L. And that's because there was an I here. So you take the imaginary part, you bring this becomes a minus I up here. So the real part of minus I times something is minus the imaginary part of that. And so that's, the imaginary part is minus I times, minus the real part. Anyway, this is what you get. And so once again, we recover the optical theorem, sigma total
is equal to 4 pi over k, imaginary part of f of k of 0. So this is another example of the optical theorem, and the point here is simply that the optical theorem works not only for elastic scattering but also for absorptive scattering. But as I told you last time, in quantum field theory, it also is a general result. It follows from the unitarity of the S matrix. And the S matrix is unitary because what we're talking about is basically e to the minus I-H-T. This is essentially the S matrix. That's the S operator. And so it's unitary, and so from that follows the optical theorem. All right, any questions about that before I switch to what I think is a more interesting topic, namely, and it's going to be illustrated by an example, namely S-wave scattering over square wave potential. So any questions about this? Anyway, this is the optical theorem. Okay. All right, let's look at the potential. It's a square well to make it easy. Now, of course, there's something artificial here. This point and that point. That's a discontinuity in the potential that may introduce some, how shall I say, artifacts, but I don't think they're serious in this case. The potential then in V of R, I'm going to take as minus V0 for R less than R0, and V of R is 0, R greater than R0. And we're going to let K0 equal square root of twice the reduced mass, the depth of the potential, divided by H bar squared. And that's going to be a constant throughout the calculation, although what we can say is we can imagine varying the potential, the depth of the potential. As we vary the depth of the potential, we'll have either, if it's very shallow, we'll have no bound states. As we lower it further, we'll get one bound state, and then eventually we'll get 2, and then we'll get 3, and so forth. Okay. Now let's analyze the scattering wave function first. As usual, we're talking about minus h bar squared over 2 mu, Laplacian minus v0. We're going to set this wave function, this is this phi of r. We're going to set it equal. I should say, we're going to be concerned only with S-wave scattering to make things simple. In fact, S-wave scattering is the only scattering that matters at low energy, because this is a potential of finite range. And you remember the Bessel functions are essentially, the spherical Bessel functions are essentially Zippo until they get to a certain distance, and at very low, and it's a function of kr. So if k is very small, then the Bessel function is the spherical Bessel function is essentially 0 out to a certain distance, and if this is only a finite range, then the limit k going to 0, only the S-wave contributes. So we're going to let this equal u over r and then some y Lm, but we're, as I said, talking just about the S-wave. So this equation will simply be u over r equals h bar squared 2 squared over 2 mu u over r. This is for S-wave. And in that case, this Laplacian, well, I've already gone to S-wave, and the Laplacian of u over r is just 1 over r in double prime. And so our equation is, after we cancel a couple of constants, it's u double prime plus k0 squared plus k squared u equals 0 for r less than r0, and u double prime plus k squared u equals 0 for r greater than
R0. Okay. So in both cases, you've got basically a sign, and then you've got the boundary condition that U of 0 equals 0. So what we've got then, let me write the solutions here to save blackboard space. We've got U of R, let's say B sine K prime R, or R less than R0. And here K prime is the square root of K0 squared plus K3. For R greater than R0, K sine KR plus delta 0. So delta 0 is the S-wave phase shift. Okay, now we want to match. So we've got a solution in here, which is a sine starting out like here and whatever. And then we've got something over here that's a sine wave of a different frequency and different wavelength. And we want to join them here. And the standard way of doing that is something you learn when you do one-dimensional quantum mechanics. And you guys, I understand, did a lot of that in the fall with David. And so a nice way to do it is to set the logarithmic derivative. So d log u dr in one region, r equals r0 equal to d log. So this is like u1, u2, dr, r equals r0. So you set the logarithmic derivatives equal. That has the advantage of canceling these constants. And so what you get is b sine K prime R. So this prime means K prime, this prime means d by dr over b sine K prime R is equal to a sine KR plus delta prime over a sine KR plus delta. And when you boil that through, what you get is K prime cotangent K prime R0 equals K cotangent KR0 plus delta 0, which we can call K cotangent alpha of K. So this alpha of K is just K0 plus delta. Okay, so inverting things, what we get is 1 over K prime tan K prime R0 is 1 over K tan alpha, and then we finally find that alpha of K is the arctan, or tan inverse, of K over K prime tangent of K prime R0. So this is these are various formulas, and I'm going to call this formula here, this formula, I'm going to call delta 0, and this one, well, this, of course, is equal to KR0 plus delta 0, and so delta 0 of K is equal to minus KR0 plus the inverse tan of K over K prime tan K prime R0. Remember, K prime is this square root of K squared plus K0 squared, and K is positive and so forth. So this is the S-wave phase shift, and of course the S-wave cross-section as 0K is 4 pi over K squared, 2L plus 1, sine squared, delta 0, sorry, it's hard to write. It's hard to write this chalk on a low level when your arm is pointed down. Okay, so that's our formula for the phase shift. But we can play with it. We can play with these equations. And it's a very cute trick. So what we want to do is we want to find the poles in S0 of k, which is e to the 2I delta 0 of k. So this is called the S-wave S-matrix element. Any questions? Remember, I, as usual, have trouble. Questions or answers? Okay, let's just note a little trigonometric identity. Cotangent x is equal to cosine x over sine x, and that is equal to e to the I x plus e to the minus I x over e to the I x minus e to the minus I x, and the 2I out in front. And we can rewrite that as e to the 2ix plus 1 over e to the 2ix minus 1. Okay, so that's what cotangent of x is. And consequently, e to the 2ix cotangent x minus 1 is cotangent x plus, wait a minute, this is minus I. All right, let me make sure I've got this right, because all of a sudden, something here in my notes was. All right, well, let's just, you guys, come on, let's all look and see what's right and what's not right.
Should it be just I instead of 2I? Because cosine over sine is...
Yeah, but sine, oh, no 2, thank you. No 2. Yeah, that's wrong. There's no 2 there. Okay. And so it's then, so this is a mark, let's just do it correctly. This is, oh, no, that's wrong. Hold on. So e to the 2ix minus 1 times cotangent x is equal to e to the 2ix minus 1 times cotangent x is equal to I e to the 2ix plus I. And so e to the 2ix times cotangent x minus I is equal to I plus cotangent x. Is that right? Is that right? Okay. I've got this as a 1 in my notes. All right, well, let's all look at this, guys.
either 2ix minus 1 cotangent x equals I 2ix plus I. So then either 2ix minus I plus cotangent x equals cotangent x plus I. All right. So I is either 2ix is equal to cotangent x plus I over cotangent x minus I.
Despite what my notes say. And turns out that's not going to matter because it's this denominator that's the essential point here. But this is clearly right. There's a mistake in my notes. Okay, so we can change this just a little bit. We can multiply top and bottom by sine x, and then we get cosine x plus I sine x. And then we have cosine x minus I sine x. And then altogether we have S0k, which is e to the 2I delta 0 of k. All right, let me erase this. Is equal to e to the minus 2I k over 0 times cosine k prime r 0 plus I sub I over. What I'm doing now is, so I skipped a step here. This, all right, I've skipped a step here. So let me put in the step that the step I just skipped then is e to the 2I k r0 plus delta 0 is equal then to cotangent kr0 plus delta 0 plus I over cotangent kr0 plus delta 0 minus I. Okay, that's the step I skipped. So now we multiply both sides by e minus 2I kr0, and that gives us this equation. And now we have this more complicated structure here. Oh, but wait, we have one more. I skipped 2 steps. That's the problem. This cotangent kr0 plus delta 0 is equal to, multiplied by k, is equal to this stuff here. So we can rewrite that as k prime over k cotangent k prime r0 plus I over k prime over k cotangent k prime r0 minus I. And now multiplying through by sines and cosines, we get this plus I k over k prime sine k prime r0 divided by cosine k prime r0 minus I k over k prime sine k prime r0. And you notice that we've got this right because we're doing elastic scattering here, and this is still unimodular because this is a phase factor, and this is this x plus iy, x minus iy, and so that's a unimodular object. So we've got the altitude. All right, this thing has poles. Now it doesn't have poles for positive k, or even for real k. But when k is imaginary, the energy can be negative. Because remember, the energy here, well, I didn't write it down, but the energy is h bar squared k squared over 2 mu. That's the energy of the process. And so when k is imaginary, the energy is negative, and that can be and then you can have a bound state. So let's analyze. Let's look at that. What we'll find is that the poles in the S matrix represent bound states, or are at the energies at which the L partial wave has a bound state. And here we just do the S matrix. Okay, so first, are there any questions before I start with the bound state? Maybe I'm going to keep these notes all together rather than separate. So now let's analyze the bound states of this problem. Of course, it's not hard to do. I remember when I was an undergraduate, there was a discussion of a problem very much like this. And the professor did the same thing as in the book that I got this out of, namely to say that it said K equal to I kappa. I'm going to say equal to I K double prime because I could never tell. I mean, it took real focus to tell his K's from his kappas. And the worst case is when you have K, kappa, and big K. And then, when we write sloppily, big K, little k, and kappa all look the same. So with primes, things are a little bit clearer. They don't look as good, but they're clearer. Okay, so for r less than r0, u of r is going to be d sine k prime r. And now k prime is what? It's what it was before, k0 squared plus k squared. But now this is equal to k0 squared minus k double prime squared, because k is I k double prime. And now for r greater than r0, what we have is u of r is going to be c e to the minus k double prime r. Remember, k double prime is positive. The continuity of the logarithmic derivatives gives us minus k double prime c e to the minus k double prime r over c e to the minus k double prime r equals k prime d cosine k prime r over d sine k prime r at r equal to r0. And so that gives us minus k double prime equals k prime cotangent k prime r0. Now, if we unscramble what that is, that's the same thing as k prime cosine k prime r0 minus I k sine k prime r0 equals 0. In other words, if we remember that k double prime is minus I k. So with k double prime equal to minus I k, this equation is this. And you see this equation is just the equation here. In other words, the bound state condition is the same as the condition for poles. So the Lth wave, or in this case the S wave, S matrix element, has poles at so let's just look at this complex K plane. So we have scattering out here, and then we have poles. Now where are these poles? They're at k to the I k double prime, where k double prime is positive, and so these are poles on the imaginary axis up here. Now, whether you have any poles, or how many poles you have, between 0 and a large number, depends on how big V0 is. If V0 is really big, you have a lot of poles. If V0 isn't so big, you don't have so many poles. So as I said before, this result is part of a pattern. You can show, this is sort of the theorem,
If the absolute value of V of R goes to 0 as R goes to infinity sufficiently fast,
and I don't remember what sufficiently fast is. Certainly a Yukawa is good enough. You don't need something that's a square well. But it may be possible to prove this if it goes faster than 1 over R to the 5th or something. I don't know what it is. But anyway, it's for short range potential. And of course, in nuclear physics, all potentials are short range. It's very probably not true for a Coulomb, but it might be. Anyway, if that's true, then the S matrix element, the Elf wave, SL of K, or as I was writing it before, S sub L of K, has poles at K such that E equal to H bar squared K squared over 2U, which is less than 0, has poles at K such that E is the bound state energy. Well, that's not the best sentence, but the point is that if your potential has some poles, then at those poles, the Elf partial wave scattering matrix, S matrix element will have poles there. Poles over here. Okay, now this, I wanted to, any questions? By the way, this this sort of algebra and analysis and complex analysis was done in the 60s, maybe in the late 50s, but mainly in the 60s, early 60s, and 1960s, of course. And you can see that it's very amusing. I mean, the idea that bound state poles give rise to poles in the S matrix. And what can happen is these poles can come over here and be near the real axis, and then they cause resonances. And so the idea that the S matrix was analytic and that the poles were bound states and that the resonances, the poles near the real axis cause bumps in the cross section and cause resonances. This all really captivated people some people in the 60s, and it's particularly true on the West Coast. People just took it much, much too far. It was by the mid 60s and late 60s, I would say that most of the theoretical particle physicists on the West Coast were doing this stuff with more and more elaborate mathematics, and it became so fashionable that the guy who was leading the charge at Berkeley, Jeffrey Chu, who had married a French woman, and his wife died and married a French woman. He was on the cover of Paris Match, or one of the French magazines, one of the popular French magazines. This wasn't some esoteric French science magazine. This was a popular French magazine. He was on the cover, big picture of his face, and his wife there also. And that's how popular this was. And then it all crashed. Including, I mean, not completely, it's obviously there's some residue that's of interest, but it's not all of physics. In fact, people went so far as to say they should throw away quantum field theory and just concentrate on the analyticity and unitarity of the S matrix. And because by S matrix they meant a function not just of K, but of several Ks. So if you had n particles coming in and n particles going out. You have an analytic function of n plus m variables. And this was very sophisticated mathematics that nobody knew. So it was part of the people who had to study it. And so it was crazy. Anyway, all right, back to real life. Let's talk about scattering lines. All right, the scattering length is the low energy limit of the S-wave phase shift. Now that S-wave phase shift is going to go to 0 as k goes to 0. So we divide by k, limit k goes to 0, and put in a minus sign for a reason you'll see. And so that's the definition. Scattering length A is minus the limit of delta 0 k over k as k goes to 0. Okay, well, let's go back to our equation right here. This equation, whoops, sorry about that. This equation where alpha is kr0 plus delta 0 is a nice equation to tell us how to find the scattering. This equation then is tangent, and let me write it slightly differently, k squared plus k0 squared, r0, divided by the square root of k squared plus k0 squared is equal to tangent of k r0 plus delta 0 of k over k. All right. Well, let me rewrite that slightly by multiplying both sides by k. There's going to be a k there. Now let's take the limit of this as k goes to 0. So both sides are getting small. Delta is going to 0, k is going to 0, so this thing is approximately kr0 plus delta 0 k. Tangent of epsilon is epsilon. And so that tells us then that delta of k is minus kr0 plus this thing. In other words, delta 0 of k is minus kr0 plus k over k0. And what's the limit of this as k goes to 0? Well, as k goes to 0, this becomes just, this denominator becomes just k0, and this becomes just tangent of k0 r0. So this is tangent of k0 r0. And consequently, using this definition, or let me rewrite this a little bit nicer. Minus k times r0 plus tangent of k0 r0 divided by k0 r0. And so the scattering length A, which is minus delta 0 over k, and the limit of k going to 0, is simply r0. Oh, there's a minus sign there. Yeah. There's a plus sign there, so there's a minus sign there. So it's r0, 1 minus tangent k0 r0 over k0 r0. So that's our formula for the scattering length. What does it look like? All right, here's a picture of it, courtesy of GNU plot. If I draw it as the scattering length at 0 is 0, it goes down, and when k0 r0 is pi over 2, it goes way down and then goes way up to infinity, then it comes back down. Until I guess this is pi over 2, and this, I guess, is 3 pi over 2, right? This is like 4.7 or something. Oh, it doesn't quite go down as far, at least not in this one. And it goes up, and I guess the sampling wasn't perfect, so it didn't go to infinity again, but it does go to infinity. So what you've got is the scattering length. What does it look like? The scattering length is negative. This is A. So A is less than 0. Then it's positive. And then it turns negative. And then it turns positive. And these turning points are where K0, R0 is equal to pi over 2, or let us say it's pi over 2, 3 pi over 2. These at least are the places where it switches from negative to positive. And so basically, so what are these points? These points where K0, R0 is pi over 2, the point here is that let's see. All right, let me say it this way. Way down here, the potential is too small. See, K0 is related to the depth of the potential. K0 there is proportional to the square root of the V0 by that very first formula way over there. So here, the part of the scattering length has no bound states. Then there's one bound state, and there's a divergence in delta K, in A. That means that this thing goes to infinity. So there's a pole in delta 0, and that's effectively meaning that we've got a pole in the S matrix. And then we've got one bound state, and it's positive. And then we're increasing it. We're still increasing the depth of the well, and I guess this is when a second bound state occurs. So let's see. Is the bound state equation? The bound state equation was, of course, this equation. Let me just get a summary from my other notes over here. All right, let's see. All right, the first bound state is K0R equal to pi over 2. I don't know why. When we analyze the bound states, did we? I've lost track. Where are the bound states here? I guess I went through this analysis too quickly and just. Right, this is the bound state equation. And K prime is this, and in this analysis, we're talking about the limit K going to 0. So this thing in the, in the limit K going to 0, this is K0 cosine K0 R0 minus I K sine, wait, that doesn't make any sense. Yeah, this K is, this K prime is actually K0 squared minus K double prime squared. All right, let me just give you the bottom line. All right, the scattering length is negative for K0R less than pi over 2. It becomes infinite when it's equal to pi over 2. Actually, these notes are wrong, because as I said, I plotted it out, and it starts positive, but then it goes negative here. The second bound state is here, but in fact, this guy's wrong actually. So it starts positive, and then shortly before the second bound state, it dips negative and then zooms up to positive, the scattering length. So a large positive scattering length indicates the presence of a low energy bound state, and the scattering length that is large and negative indicates that a bound state is about to appear. So that's what we see down here. Bound state is about to appear, bound state is about to appear, and here the thing is positive, the bound state is here, the bound state is here. Okay, we have time for another example, but an example we can do very quickly, namely, let's consider scattering off a hard sphere. This is easier to do. We have V of R equals 0 for R greater than, let's say, R, and V of R equal to infinite for R less than R. So for R greater than R, we have U of R is some C sine KR plus delta, and for R less than R, we have U of R equal to 0. So, what is the condition? The condition is that this wave function has to be 0. Sorry, this is supposed to be little r. That's actually a typo in the text I got this from. So what we want is K R, the radius of the hard sphere, plus delta 0 to be equal to n pi. And so for K sufficiently small, delta 0, well, delta 0 in other words is minus KR plus n pi. And if we're looking at sufficiently small k, then n is equal to 0, and the scattering length A, which is minus delta 0 over k, is simply r. So that's the scattering length for a hard sphere. It's just the radius of the sphere, and that's why in the scattering length there was a minus sign here. That's the reason for the convention that there's a minus sign here. All right, I guess I guess that's just about that. A few more things maybe I can say here. So the low energy cross section here is certainly going to be isotropic. It's basically an S wave, and so the low energy, the sigma total at low energies is 4 pi a squared. That turns out to be the actual cross section if you go through the rest of the calculation. And and this in fact is, we can sort of figure that out from this formula over here. The elastic, let's forget about absorption. The elastic cross section then is pi 2L plus 1 over k squared. We're just looking at L equals 0, so it's pi over k squared. Wait a minute, that's the total cross section. Where is this? The cross section for simply delta L, I mean, for just the L partial wave. Yeah, the L partial wave is, in other words, sigma sub L is 4 pi over k squared, 2L plus 1, sine squared delta L. And so for L equals 0, the elastic is 4 pi over k squared delta L squared. You see, because sine delta L is small, so this is sine of delta L is just delta L. And delta L over k squared is just a squared. So this is 4 pi a squared. Okay, so that's what this comes from. Notice that this is 4 times the classical cross section for a hard sphere. Classical, sigma classical for the hard sphere is just pi a squared. Pi times A is R. So this is R squared, and this is also R squared, and this is R squared. So classical is pi R squared, quantum mechanically it's 4 pi R squared, and this is the S wave partial wave. Okay. And now, there's another parameter called the effective range. And let me tell you what that is. K cotangent delta of K. And that is minus 1 over the scattering length plus a half R0 K squared. So that R0 is called the effective range. Unfortunately, it's the same variable as I used as the radius of the square world potential. So this is called the effective range. So that's, in other words, what we had here was this minus 1 over A is the first term, this being the scattering length. The scattering length was the first term in the expansion of K cotangent delta. And when you add the second term, that brings in the effective range. And the scattering amplitude, in fact, f of k, this is all And that you can show is 1 over k cotangent delta minus I. And then if you use this expansion, what you get is minus A over 1 plus I Ka. So that's the expression for the scattering amplitude. And if you put, so that's the scattering amplitude. If you just use the scattering length, if you put in the effective range, then this is minus A over 1 plus I Ka minus a half or 0 A K squared. So that's the better formula that you get for the scattering amplitude. And conversely, if you analyze the S-wave scattering amplitude, you can figure out what this, experimentally, you can figure out what the scattering length is and what the effective range is. Any questions? You can see how beguiling this can be. I think we ought to start new subject pretty soon. So I think maybe Monday I'll start with quantizing electromagnetic, maybe do time-dependent perturbation theory and quantizing electromagnetic field and see how photons can interact with, say, a hydrogen atom, which we understand, and maybe do some other things. Okay, why don't we stop the thing, assuming that it's right.